Okay, class, here's the simple linear regression example that we did in class. I'm going to record it one more time so that you can take a look at it if you need to. So we have advertising expense and sales. So sales is what we're trying to predict. Right? This is sort of this is our Y. This is what the notes talk about how Y is often something that that we don't have a lot of control over, or that we don't sort of fully understand what's going on here. And then advertising expense. So advertising expenses are X, and it is something that we have control over, right? So if we own this company, we can spend however much money we want on advertising to some degree. And then so that is every quarter or every month or something, they tracked how much they spent on advertising and then recorded how much sales they got for that month. And then that's what we have here. So it's a pretty small data set. And so we can a couple ways to get the linear regression out of this is we can highlight it all, go into insert and scatter. Right, so we want to include a scatter diagram. So get something like this. So we want to make sure that our X and Y's are right. So remember, sales is our Y, and so that should be over here on this side, so it looks like it's right. So I'm going to clean up this a little bit. I'm going to delete this guy. Go into layout, access titles, and then stick in this guy. And remember, if I hit F2 and then equals, and then I can click on a cell, and then it'll just appear over here, right? So then if I change this over here, like advertising expenses, then it changes it here. So that's kind of cool. Let's change it to advertising expense, and then let's do the same thing. Click on it again. Go to this is let's see layout. Chart axis, do the horizontal. And same thing, F2 equals sales. Like that. Okay. And we can clean this chart up a little bit. In fact, I don't really like all those guys. Let's get rid of those things. Let's call this sales by advertising expense. Something like that. Okay, so that looks pretty good. So let's add the trend line. Let's get the line that goes through all these points. And how we do that, we click on any of the points, right click, click on Format Data Series. Nope, that's wrong. Try again. Click on the buttons, right click, say Add Trend Line. We're going to leave it as the linear. We're going to click on Display Equation on Chart, display R-squared value on chart. So later on we might play around with some of these guys, some of these other ones. Right now we're just going to stick with linear. Click close, and there we go, we got it. So then you can grab the equation and sort of put it somewhere else if you want. In fact, you can even change this. So we could put it in the format that we're used to seeing. Something like that, right? That's how with the book how our notes show it, that we have the intercept first and then plus the slope times x, right? And x is advertising expense, right? Here's our R-squared value, so that's good. All right, so if we wanted to do this and get some more p-values and that kind of stuff, we go into data and then data analysis. Remember, this is an add-in. Click on regression. Okay. For our y range, figure out what's y. Well, sales is y. Our X range, advertising expense. We have labels, so let's check labels. Confidence intervals, we want confidence intervals. Let's leave the residuals there so we can see what they look like, and then let's find where we want this. Put it right there. And click on OK. Okay. Move this guy just a little bit. Okay, so a review of what we have here. So we have this multiple R, where this is actually the correlation coefficient. So we get, or the absolute value of that. So we could actually check that. We could do this correl function with these two, right? So here's that correl with this. So those two numbers are the same, only with simple linear regression, meaning this multiple R is the correlation coefficient if we're doing a simple linear regression. If we're not, then it's just the square root of the R squared. So here's R squared. Here's adjusted R squared. So for a simple linear regression, adjusted R squared doesn't really mean very much because it's really just adjusting for the number of variables. But we only have one variable, so it doesn't matter much. Standard error and observations. So this ANOVA, remember, tells us the overall significance, the significance of the overall model, whether or not the model as a whole is significant. And the only one we're really concerned about, that we care about, don't care too much about what these numbers are, but what we care about is this value, and this is a p-value, right? The significance f. This is a p-value, and it's 0.03, so it's less than 0.05. So we would say, okay, well, the model as a whole is significant. And so that's good. So we have to first sort of glance at that and make sure that's okay. And then here we have the intercept and the advertising expense. Here's our coefficient, which is like the B's in our formula, right? These are the B's. Calculate a standard error and do a t-test for each of these. So this is just like what we've always done, or what we've been doing the last few weeks. We can figure out the standard error and then figure out a t-statistic and figure out a p-value, the probability of this t-statistic, given some null hypothesis. And the null hypothesis is always that these variables equal 0, right? So if the variable equals 0, what's the probability of this t-statistic happening? That's what this p-value is. So we're not too concerned that the p-value is not low for the intercept. All that is saying is that there's no evidence that the intercept is not 0. But we don't really care if the intercept is 0 or not. It doesn't make a whole lot of difference whether the intercept is significant, because it's just a number. It doesn't matter. We are concerned about this advertising expense, so whether or not these B's or these X's, are significant. In this case, we have a 0.034. So as you can see, these two are the same. We pointed this out in class, and that's because there's only one variable here. So the hypothesis of this guy is that there is at least one variable that's significant, essentially. And, well, there's only one variable. Excuse me. So that's why. Okay, so that's it. So the only other thing I wanted to show you about this one was this residual output. So what this does is it takes every observation, so there's only 6 observations, figures out what the y hat is, this is predicted sales, it's y hat, right, and then finds out the residual, which is what the true y is minus y hat. So I'll show you this. We did this in class. If I copy and paste this up here, it kind of makes more sense. So here's our true y. So you can hear this is y. Predicted sales then is y hat. Right. This is what the y we got according to our according to this formula. And so if we plug in this x and we say 800 times 10 is 8,000 plus 4,000 is 12,000. So that's what predicted y hat is, predicted sales. But our actual sales that month was 15,000. Right? So the difference is 3,000. That's the residual. So we can actually see this on the graph. So if we find this 800, here's 800, and 1,500 right here. So the line says, well, it should actually be right there, right? 12,000. 12,000. But instead, it's up here at 15,000. So the difference between, if we drew a straight line straight up to here and then measured that line, it would equal 3,000. That's all that's saying, right? And it's pretty easy to see. So it's just, the actual minus what we got. The actual minus what we predicted is 3,000. So we do that for all of them. This number is essentially 0, so 5,000, 5,000. So that's this point right here, right? It's actually on the line. Yep. So that's 0. So we're going to use these residuals later on, but that's all that means. Okay, so that's that one.